Okay, can you hear me?
Yes.
Yes. Today I'm going to be talking about our work on the development of an artificial kidney. Just some disclosures. The project was supported in part by a company we started several years ago called U.S. Kidney Research Corporation. I'm a board member, a shareholder, and I'm medical and scientific advisor of the company. And we're also working with the University of Arkansas on the development of this device. Now, as far as current dialysis modalities, dialysis changed nephrology from a palliative care specialty where patients uniformly died to a chronic disease management specialty that allowed the development of kidney transplantation to take place in the 50s. Hemodialysis has been around for 60 years or so, peritoneal dialysis for about 40 years. And the dialysis space has been stagnant for some time now with very little new developments. As far as the history of hemodialysis, it was really in 1854 that a Scottish chemist whose name was Graham published an important paper in the Royal Society on the diffusion of liquids. And he also made fundamental discoveries in the process of dialysis. In 1861, he actually coined the term. It comes from the Greek dialin or dia, which means apart, and leon, which means loosening. In 1913, Abel, Rowntree, and Turner dialyzed animals, and they directed their blood through colloidal membranes. These are cellulose-like membranes, and they used this compound called hirudin, which they got from the saliva of leeches, which functioned as an anticoagulant before heparin was devised. In 1924, George Haas in Germany actually performed the first human dialysis treatments, and by 28, he had dialyzed an additional 6 patients, all of whom died. He also used hirudin initially, but because of severe allergic reactions, was finally changed to heparin. And here's a picture of him at the University of Gießen dialyzing patients. The whole story of dialysis really changed when William Kolff got into the act, and he's considered the father of dialysis. It was during World War II that he moved to a small hospital in Camp in Holland to escape the Nazis who had invaded Holland and had been put in charge of his original hospital in Groningen. And at this smaller place, he began work on the first dialysis machine after watching a young man die of renal failure. He started bench experiments with cellulose sausage casings shown below here. These are casings that sausage was kept in. And he did some in vitro experiments with saline and urea. He also circulated uremic blood through the tubing that he put on a motorized drum that was sitting in a stationary water bath. Here's one of the devices he created. And in 1943, his rotating drum device offered effective treatment for the first time in AKI. The membrane was 2 to 2.5 meters square, which is similar to what we use today. To start the treatment, he drained the blood from the patient into a sterile jug, added anticoagulants. He hung up the jug and then let the blood go through this sausage casing that was wound around the wooden drum. The device was also primed with 1.5 to 2 units of blood from the blood bank. There was no blood pump. The rotating drum was on an electric motor, and gravity moved the blood. And then the clean blood went into a second jug that he raised, and the blood then was returned to the patient, and it took about 6 hours to do a treatment. Then at the Peter Brent Brigham Hospital, George Thorne, who was the chairman of medicine, invited Kolff to work there with Carl Walter, a surgeon, and John Marrow. John Marrow is really the creator of the specialty of nephrology, to redesign this rotating drum machine. And this new version also supported the first U.S. kidney transplant program. The first patients were transplanted in 1954. This is shown down here. Merrill is shown here in the lab coat, and these are the Herrick brothers, Richard in the middle and Ronald on the right, who was the donor. Richard lived another 8 years after receiving the kidney. Again, the sausage casing was used, wrapped around the drum, but this time the blood was connected to latex tubings attached to the patient's bloodstream. And this is a picture of the Kolff Brigham dialysis machine in 1948. Then the device was built by Edward Olson, who made another 40 devices and sold them for about $5,600 in 1950. After this work, Kolff continued to work on the artificial lung, the artificial eye, and some of you may have heard of the Jarvik heart several years ago. Kolff was actually a mentor with Jarvik. As far as peritoneal dialysis, it was 1550 BC where the first recorded reference to the peritoneal cavity appeared in the Ebers Papyrus. Peritoneum comes from the word peritoneon, which means to stretch around. In 1826, Dutrochet first described the process of osmosis. In 61, I had mentioned Graham. He described the differences between crystalloids and colloids. Wegner in 1877 showed in animals that if you put a hypertonic solution in the peritoneal cavity, the cavity increases its volume. In 1923, Ganter first used PD clinically. He installed hypertonic saline in 2 patients with renal failure. In 1927, Hauser and Werder tried peritoneal lavage. They used 2 different catheters, one for inflow and one for outflow, in patients with mercury poisoning, but they all ultimately died. In 46, Frank, Seligman, and Fine reported the recovery of a patient with acute renal failure after 4 days of peritoneal lavage. And then in 1959, Rubin was the first to report using PD successfully in a patient with end-stage renal disease who survived about 6 months. In 1962, Lasker invented the PD cycler, which we still use today. In 1968, the Tankoff catheter was created. It had 2 Dacron cuffs, and it was really a paradigm shift in PD. In 73, Babb showed evidence for bidirectional flow between the blood and the peritoneal cavity and the peritoneal cavity and the blood. In 78, Popovich and Moncrief, basing it on their work on theoretical mass transfer, put into practice a new approach to PD that eventually became known as CAPD. In 78, Oreopoulos first used solutions in plastic bags instead of bottles. And in 1980, Buon-Cristiani developed the Y set, where the inflow and outflow are in the configuration of a Y, and this was the single most important factor in preventing peritonitis in patients. Another milestone has been the involvement of the federal government in kidney innovation. In 2016, the White House had an organ summit that called for increasing breakthroughs in research to improve outcomes in patients needing transplants. In 2019, the Kidney Health Initiative publishes what they call their technology roadmap for innovative approaches to renal replacement therapy. In 2019, the Kidney X contest was established. It was a first of its kind public-private partnership between HHS, the Health and Human Services, and the ASN, providing prize money to engineers, scientists, and other innovators to completely disrupt the way kidney failure is currently treated. In 2019, the FDA approved a breakthrough devices program in which technologies for mobile dialysis was considered a priority area for biomedical engineering. In 2019, the president issued an executive order advancing American kidney health, and part of the policies that were stated was the development of an artificial kidney. Now, in the last few years, a number of different entities are working on what is called wearable peritoneal dialysis, and they all have the same configuration, which I'll describe in a minute. There's a number of groups. There's something called the AWAC in Singapore, the WEKID in the Netherlands, Renard in Russia, VIWAC in Italy. Fresenius is working on a device, and then there's EOCART in South Korea and the US. And basically, they all have a purse-sized controller with batteries that are carried by the patient. And there's a disposable cartridge. The key of the device is the disposable cartridge that rejuvenates the used dialysate. So instead of flowing 2 liters of solution in every 2 hours, you basically use the same dialysate that is cleaned by this cartridge. And there's a small pump, and the volumes are much less than we typically use, about half a liter. The devices automatically remove dialysate, they regenerate it, at least that's the goal, and infuse it back into the patient. And the process is repeated several times per hour, and the cartridges last about 7 hours and they need to be changed. And then periodically the patient infuses fresh dialysate. So the idea behind these devices is that in addition to using them at night or rarely during the day, patients can use this all the time while they're ambulatory. People are also working on wearable or smaller hemodialysis machines. Actually the first device was reported in 1976. It's not well recognized, where they created, they basically shrunk down the dialysis machine and made it portable and wearable. But I don't know of anything that came of that. Dr. Gura at Cedars has been working on a portable hemodialysis wearable device since the mid-2000s. This is a picture of it here where it's worn around the waist. And then other groups like Next Kidney in the Netherlands are developing a suitcase-sized machine. And Quanta, a company in the UK, are developing a tabletop machine that they call the SC+. There are some problems with the WAC that are listed here, and a lot of them are advancing, and we'll see where this device ultimately gets. But there are a number of issues with this device that are currently being worked on as listed there. One of the issues with these wearable devices is the need to get rid of urea, and there's different ways different groups are working on this problem. One of the ways is by using this new compound called a mixene, which is a titanium carbide based compounds. They have a very high affinity for urea. And so basically they bind the urea and then you get rid of them and then replace them with fresh mixenes. People are also using the enzyme urease, which breaks up urea into ammonia and carbon dioxide. And other ways are to put a current through the solution, electrooxidation, which breaks down the urea, and some people are using very intense light. It's called photooxidation with titanium oxide as a catalyst, and the reaction products are nitrogen and carbon dioxide. And other people are using thermolysis, which basically involves heating the solution to over 150 degrees, and this breaks up the urea also into ammonia and carbon dioxide. So this remains one of the technical issues that have to be solved in order to have a viable wearable either hemodialysis or peritoneal dialysis device. Now, other people are using biological approaches, such as UCSF, and they're working on an implantable artificial kidney. It has two components, one a non-biological component, which is their ultrafilter, which filters the blood, their silicon ultrafilter, and then they have another component they call a bioreactor, which has cultured cells. And there are several problems with the idea of using cells. First of all, the kidney has about 45 cell types, each of which have different transport characteristics. And when you put a cell in culture, they don't retain their properties in vitro that they had in vivo. No one has replicated all the required cell-dependent transport properties in vitro that the kidney does. And also the cells need to function for a long period of time, not just for a few days, even if you could get the same functionality. The other thing is that the function of the kidney is not one-dimensional or two-dimensional. There's the three-dimensional spatial organization provides the functionality. Then there's also issues of rejection if the cells aren't derived from the same patient. So far, they've used pig kidney cell line from the pig proximal tubule, but this line does not have the transport properties that are needed to make a viable artificial kidney. So that's where this stands right now. The NIH has a program called Rebuilding a Kidney Consortium, and they're funding a lot of different groups to actually create a kidney from scratch using stem cells. But it's the same problem, the problem of generating all the functionality that the kidney has using cells and having the cells exist for a prolonged period of time. As I always say, it would be easier to build a 747 from stem cells than it is to build a kidney. Other companies, such as Mural Matrix, are taking a different approach. They're taking pig kidneys and getting rid of all the cells. So they have now this extracellular matrix scaffold. And then what they do is, or they're trying to do, is put human stem cells back into the decellularized structure, and then have the cells regenerate the cellular architecture of the kidney. Same problems. You have tons of different functional cell types. The cells in this case have to actually know where to go, which is harder to believe it's ever going to work and function for a long time. And there's rejection issues. This is a little movie showing the stem cells going into, I think this is a liver. They don't say on their website, a decellularized liver. And then there's the Xenotransplant story. George Church and Luhan Yang founded a company called eGenesis, and they've done some major work in this area. There's two major issues. First of all, you have porcine endogenous retroviruses called PERVs that are incorporated into the pig genome. And people are very afraid of transplanting pig organs into a human because you could potentially now have these retroviruses activated within the recipient. But in 2015, Church and Yang knocked out all the porcine retroviruses in cultured cells in 62 different sites in the genome. So that was a big advance. And then in 2017, they actually created PERV-free pigs. So these pigs do not have any, at least of the known endogenous retroviruses. So that was a big advance. We're still left with the problem of rejection, and there's hyperacute and acute, let alone chronic. But as far as the hyperacute rejection, people feel that the alpha-gal antigen is primarily responsible for the major responses one get. And people have knocked out the alpha-gal antigen, and the hyperacute rejection is minimized. People are still working on the acute rejection. A company called United Therapeutics has actually been created by Martin Rosenblatt. Martin created Sirius Radio, and his daughter has pulmonary hypertension. So he's been interested for a long time in creating xenografts that would supply the lung, but obviously other organs too. And he's put hundreds of millions of dollars into this. So xenotransplants are still being worked on, but they're likely going to be solved in the future. Another biological approach is a chimeric approach. In this particular example, pig-human endothelial cell chimera. This paper was just published, and the idea here is to take a pig kidney and not get rid of all the cells, but just get rid of the endothelial cells lining all the blood vessels. So they have ways of doing that with different detergents. They perfuse the kidney, get rid of all the endothelial cells, and then they take a human placenta-derived endothelial cells and perfuse the kidneys. And then it turns out that the kidneys then reline all the blood vessels with human endothelial cells. And the thought is, well, perhaps this organ won't reject or have a severe rejection, because basically all the blood vessels are seeing human tissue. And, you know, these placental cells could be pre-screened for ABO and HLA compatibility before they're infused into a donor organ. So the thought here is that one doesn't have to create an entire pig kidney from a pig and get rid of the PERVs and certain HLA antigens. One can use that organ, but just replace the endothelial cells. So this is a cute idea that is currently being worked on. When we started thinking of this project, we took a lesson from the Wright Brothers, who, when they were designing an airplane, chose purposefully not to use biological materials. And what was done instead was to scientifically determine the principles of flight and use those principles with man-made materials to create, in this case in 1903, the first powered controllable airplane. And today we have the 787 because of it. So we took the same approach and decided not to use biological approaches. But in thinking of the problem, breaking it down in an engineering sense, these are the functional requirements that are needed to create an artificial kidney. First, you have to have an ultrafiltrated blood. and prevent the filtration of cells, albumin, and globulins. Secondly, you need to prevent the filtration of glucose, but allow the excretion of urea, ions, and water. Thirdly, you need to be able to excrete sodium, potassium, chloride, bicarbonate, calcium, magnesium, and phosphate equal to what your net dietary intake is, and also have this occur dynamically, because we're constantly changing the chemistry of our blood when we eat, and such a device would need to respond to the changes so that the input and output are always equal to minimize the fluctuations in blood chemistry. And the same concepts for water. The output has to roughly equal the patient's water intake, plus this equality has to change dynamically because of our different drinking habits. It would be nice if such a device also had functionality as far as middle molecule excretion, given the thought that there's some middle molecules that create toxicity and uremia. And because it would be implantable, one cannot use external water, dialysis, or a dialysate. And in thinking about everything that needs to be done, creating an artificial kidney is significantly easier than creating an artificial heart, where one basically has to create an efficient pump, or an artificial pancreas. There's many more functions that need to be satisfied in creating an artificial kidney. So we decided to not only not use cells, but to devise a technology that does not utilize dialysis, water, or a dialysate. In thinking about the amount of water used, there's about 6.2 billion gallons of water used per year in hemodialysis, which is enough to feed all the livestock in America for a year. It's not well realized how much water we use. So we began in 2016, and the device conceptually has 4 different modules. First, there's an ultrafiltration module, and I'll discuss each of these. There's a nanofiltration module, an electrode deionization module, and a reverse osmosis module. So what are these, and what do they do? This just shows some early bench experiments with the different components. The ultrafiltration module filters the blood and prevents cells and proteins from getting into the rest of the device. That's actually this guy right here. The nanofiltration module prevents glucose from getting into the final synthetic urine, but allows urea and ions and water to get through. And that's a complex problem, because urea and glucose are quite similar as far as their physical properties. This is the nanofiltration module here. And then there's other components called electrode ionization modules. These are the parts of the device that do the ion transport. So you can think of this like the nephron, transporting the different ions. That's this component here. And then there's a reverse osmosis module that does the final water transport to ensure that the final volume of water coming out of the device is roughly equal to the patient's water intake. And this is a more detailed view of the flows between these components. And it's a little complicated, but I'll take you through it. So here's the input stream that would represent blood, first going through the ultrafiltration module. And the ultrafiltration module, again, prevents the cells and the proteins in blood from getting through and sends them back to what's called here the venous stream. The rest of it goes to the first component, which is called EDI1. This is an electrode ionization unit that's set up to handle mainly potassium. From there, the solution either goes to the nanofiltration unit or goes to the reverse osmosis unit that handles the water, which is the final unit actually, before going into what we call the urine stream, this synthetic urine stream. After the nanofiltration unit, there's a second electrode deionization unit that handles the other ions. The outflows from that are actually 3, back to the venous stream, to the reverse osmosis unit, and some of this recycles back to EDI1. In addition to these components, there's other things that make the device work. There's ion sensors that monitor the concentration of ions thereby providing feedback control so we can modulate the functionality of the device. There's pressures, flows, and current sensors, and there's other valves and stepping motors. The device is run by a Raspberry Pi computer board, and there's an Arduino Do input-output board that takes the information, pressures, flows, and ion concentrations, and sends it to the computer to make decisions as to what to do under different conditions. And we've written software also that allows this whole thing to function. This is a more detailed view, which I don't expect you to understand, but just to show you the complexity of the flows and the different components of the device. And after the talk, I can go into more detail for those that are interested. So just to show you some of the functionality of these different components, this is the ultrafiltration module. And initially, when we were devising it, we used a polysulfone membrane. And these are just some of its ultrafiltration properties, looking at the different components of blood. And the rejection, this is showing the lack of filtration at different time points. And you can see that it was rejecting the cells from getting through quite well. And this is just a pictorial view of that. This is the blood coming in. This is what comes through the membrane. And it looks clear because there's no red cells. And then this is what didn't get through the membrane and would be returned to the so-called venous side of the device. Some experiments looking at longer term functionality because membranes can foul. What one sees is an immediate drop off. This is measuring the flux, the water flux in mils per minute per meter squared per PSI, which is the pressure gradient across it. And you can see it's at least constant in this particular experiment for up to 15 days. And also we looked at the ability to reject albumin. We don't want albumin or globulins to get through. And you can see the rejection was quite good over at least this time period. Now, since that time, we've developed a new nanocellulose ionic liquid membrane that we call the NCILM. And this membrane has superior characteristics. A patent is pending for this membrane. This is a scanning EM of what it looks like. And this is what we will be using ultimately in the device instead of polysulfone. This table is complicated, but it just shows parameters that we looked at comparing the NCILM here in blue to other commercially available membranes. The PS is a polysulfone membrane that we made in the lab that we're studying. But if you focus here, and the pressure across these membranes was around 2 bars, pretty comparable. But if you look at the water flux through, you can see how much more flux comes through the NCILM membrane. It's much more efficient as far as its filtration properties. And also much better than the others as far as this last column you could focus on is the ability to reject albumin, meaning not letting it through. You can see it has superior albumin rejection properties, although the others are quite good also. And so we're pretty happy with this membrane. It also has better, we use lysozyme to test its ability to reject the permeation of middle molecules. There's a number of middle molecules. Lysozyme has a molecular weight of 14,300 kilodaltons. Beta-2 microglobulin, one of the hypothesized uremic toxins, is around 11,800. Light chains are around 25,000 daltons. So we use lysozyme as a molecule that's roughly in that same category as far as size. And it really lets the lysozyme through. The rejection is 0 compared to the polysulfone membrane that we had made initially. So we're pretty hopeful that this membrane will also have favorable characteristics as far as being able to get rid of some middle molecules. We'll see. Now, another component of the device is what's called Electrode Ionization, or EDI. And it was really Katz in 1956 at this company Ionics who created the first workable device. He presented a paper at the International Water Conference called The Present Status of Electric Membrane Demineralization. And I'll take you through this. It's a little bit complicated, but basically what this device does is when you put an electric current through it, you can actually make ions go from one solution to another. And there's several components to these devices. First, in the center here, you have cation and anion exchange beads. So you can think of it like Kxalate that we use clinically. It exchanges, the cation exchange beads exchange one cation for another, and the anion exchangers exchange anions. The purpose of these is really just to enhance the flow of these electrolytes through the device. It enhances the efficiency of the flux. And then on each side are different membranes. One is a cation exchange membrane that's permeable to cations, and on the other side is an anion exchange membrane. And so what you do here, if you focus on the left, is to put a solution, complex solution in with a bunch of ions through it. And what you do when you turn on the device, putting a current across it, you end up driving the cations into one solution, which is a concentrated solution of cations, and you drive anions into another output from the device, which is a concentrated solution of anions. And then in the center here, you end up with water without ions, a very pure water product. And this device now is actually used commercially by many companies to make water that we drink. So it's used throughout the world, electrode ionization. And when I was thinking about this originally, I thought this might be a neat component of our device, because basically we have a potential mechanism now for transporting ions similar to the nephron does under computer control. And we've actually taken this technology and revised it, and we have a patent on what we've done, and we call what we've created multiple mesh activated wafer electrode ionization, or a WEDI for short. And this is just a picture of one of these devices. And the unique thing about this, as opposed to other electrode ionization devices, is it combines multiple ion selective resins into one device. So we have sodium selective ion exchange resin, a potassium selective, calcium, magnesium. What this allows you to do under computer control is to selectively choose the transport, the ion that you want to be transported alone or in combination. It provides functionality and also saves a lot of space compared to having a different EDI unit for each of these. And again, this is a detailed slide. I don't expect to go over all the details, but in order to decide what resins to use, one has to do a ton of experiments looking at many different resins, because they have different selectivities for sodium, potassium, calcium, chloride, and magnesium. And assigning sodium 1, this just gives examples of different resins and their relative selectivities of these ions over sodium. And this is a formula that is used to calculate the selectivity. So the simple take-home message from here is that you have to pick correct resins, which is a lot of work. And secondly, another interesting thing about these devices is the selectivity is not fixed, but by changing the current here, just going from 0.02 amps to 0.04 amps, you actually can change the selectivity. So you can see here, looking at the selectivity of this W1 resin, changing the current from 0.02 to 0.04, change the potassium selectivity from 2.1 to 1.39, or with this resin here, changing it from 3.3 to 1.6, or magnesium from 4.56 to 1.98. So we can actually take advantage of this by altering the selectivity by changing the current. So the current doesn't just change the rate of transport, it actually changes the type of ion that you preferentially transport, and we can take advantage of that in the functionality of the device. And this just shows some experiments with the WEDI looking at bicarbonate and phosphate. And again, at 0.02 amps and 0.04 amps. And you can see here at 0.02 amps versus 0.04, you get much more transport of bicarbonate. Whereas interestingly, with phosphate, it's inverse. When you increase the current, you get less phosphate transport. So you can't predict what's going to happen. It's empirical. But again, you can take this kind of observation advantageously in designing the devices. And this is an interesting experiment just showing the capability of the device to regulate the potassium concentration. So in this experiment, we're putting in a solution with a potassium of 4, and then we spike it up to 17 millimolar, which is obviously not physiologic, and then watch the device transport the potassium and bring it down close to its original range. And here we did it over 2.5 hours, but it can be done much more quickly as needed. And again, we have the feedback system where the potassium is being sensed, and the computer can alter the functionality of the device to alter the rate of transport to return it to much more quickly if needed. We're also working on enhancing the potassium selectivity of our devices. We're using chemistry called crown ether chemistry. This is a picture of Donald Cram at UCLA. He won the Nobel Prize for this chemistry back in 1987. But basically what we're doing is we're attaching these crown ethers here, in this case, 16 crown 6, to the cation exchange beads, where we're coupling the amino group, this 4-amino benzene derivative of the crown ether, to this carboxyl group on the cation exchange bead, so that we have an amide bond here which won't come apart, and then run the device. And you can see here the solid line here is the transport that occurs without the crown ether, and then the dotted line is, or excuse me, it's the other way around. Without the crown ether is the dotted line, and the crown ether is the solid line. So you can see the enhancement of transport when we have the potassium selective crown ether there, and sodium didn't change very much because the crown ether doesn't bind sodium. So we're going to be using this crown ether chemistry to enhance the selectivity of the device for calcium, magnesium, and other ions also. So another requirement with the device is that it doesn't allow glucose to come through. Remember, glucose is getting through the first ultrafiltration module, and so we can't be excreting glucose into the final synthetic urine stream here. And so what we do to prevent glucose from getting through, which is a difficult problem because we have to let urea through, and again, they're similar in size and chemical properties, is we use a membrane called a nanofilter. And the nanofilter has the property of being pretty impermeable to glucose if you can use the right filter. And we've done a number of experiments with different filters, but this particular combination of using 2 of these NF270 filters has a good glucose, fairly good glucose rejection rate, but lets urea through. So this is an important milestone because otherwise glucose would just come straight through the device and will be excreted in the urine. And this shows some experiments in the last component of the device, the reverse osmosis module, which transports water, and just showing that we can vary the water transport here in mils per minute per meter squared by changing the pressure gradient across the device. And we've studied a number of different membranes. What we don't want is that ions will go through it and glucose, and you can see that's pretty good. We still have a problem with urea. Most of the RO membranes that are commercially available let urea through. And so we're losing urea back out of the synthetic urine stream back into the so-called venous stream. There are RO membranes out there that people have created that are pretty urea impermeable. We have not tested those yet, but we need to. So this is something we're working on over the next year to get this urea rejection back into the 90s to prevent urea from getting back into the blood. And this slide just shows a summary of looking at the excretion rates of various substances compared to the native kidney in milligrams per 24 hours. So this shows sodium. This is the range of excretion depending on the dietary intake, potassium, calcium, chloride, urea, and creatinine, and this is the device compared to the native kidney. So it's pretty good. Urea as I said, is less just because of the urea flexing back across the RO membrane, and creatinine is lower than we'd like. But again, these are not toxic substances. So in the ultimate device, if we get these kind of excretion rates, the patient's BUN will be, 2 or 3 times normal, and the creatinine will be roughly the same range increase in the blood. It won't be toxic for the patient. And this is an experiment, an in vivo study in a pig, where the device was hooked up, and basically it was a short experiment, basically looking at the ability to keep the BUN constant. The kidneys were removed, and the device was the only way that urine could be made. And you can see that over the period of time here, in the absence of native kidneys, the BUN was kept relatively constant. And this is the urea concentration in yellow here in the urine going up with time. So it just shows the ability here of the device to provide enough functionality, at least from this parameter, over this short period of time in the absence of native kidneys. So currently, the components fit into a backpack. The dimensions are about 16 inches in length, 10 in width, and 20 in height, and the device weighs 12 pounds. This shows all the components laid out here linearly, and I won't go into each of them. And this is a CAD drawing of the different components, and I'll be showing a movie later that goes into more detail to give you a better feel of the complexity of the device. So this is the movie now.
The function of a kidney while still fitting within a backpack to enhance the patient's quality of life. While the device consists of many different functional modules, the combination of sensors and smart software allow an easy interface for doctors to view patient data and patients to manage small changes to accommodate their daily activities. The purifying process begins with blood flowing from the patient through a catheter, as shown in red on the top right. It then flows to a peristaltic pump and enters the ultrafiltration module, which is shown as a cylinder on the far left. This module retains proteins, white blood cells, and red blood cells to be returned to the patient's bloodstream through a separate catheter, as shown by the red stream returning out of the top left. Our system uses a unique nanocellulose membrane, which allows for minimum fouling as well as a high flow rate. The module allows smaller substances dissolved in blood, such as glucose, urea, and ions, to pass through, as shown as the blue stream leaving the bottom of the ultrafiltration unit. From there, the stream flows through a sensor bank to analyze the patient's initial ion and urea levels to determine the removal amount using the smart software. Next, the stream is pumped into an electrode ionization module, which is shown as the blue flow into the top left rectangular module. The electrode ionization module uses an electrical potential to selectively transport various ions, mainly potassium. The ion-depleted stream is then sent to a level sensor to monitor the flow rate and pumped into the bottom port of the nanofiltration module, which is shown as the second cylinder on the right. The nanofiltration module is used to separate glucose, which needs to be returned to the body, from urea, which needs to be excreted in the urine. The stream with the concentrated glucose is returned to the body through the catheter. The stream with the concentrated urea is shown as the blue flow exiting from the top. From there, it is sent to the activated wafer electrode ionization, or a WEDI module, which is shown as the rectangular unit on the top right. The WEDI module contains multiple wafers that are selective to different ions. This allows for ions to be transported in different amounts depending on changes in the patient's blood chemistry due to alterations in dietary intake. The smart software calculates the amounts of different ions that need to be removed based on input from the sensor bank. The stream with the ions removed is then returned to the patient's bloodstream. A second stream, which contains the concentrated urea and ions for removal, is recycled back to the first electrode ionization module, where it picks up the potassium that needs to be removed. This stream is then pumped through a level sensor to determine the flow rate, and then to the reverse osmosis module, which is shown as the cylinder on the far right. The reverse osmosis module is used to prevent excess water loss in the patient and to concentrate the synthetic urine stream, which contains the urea and ions for removal. The flow comes into the bottom of the unit, and clean water is sent out the top and back to the patient, while the synthetic urine stream is sent out of the bottom for disposal.
So I know that's complicated, and I don't expect anyone to be able to master that quickly, but it gives you an overview of the complexity of the current device. Now, there are additional applications of our technology, in addition to the portable, we call the portable artificial kidney, and ultimately the implantable. The technology could also be used in a standalone device that could replace current dialysis machines, and again, not need the vast water infrastructure that is coupled to current dialysis. In addition to the water infrastructure, people have written numerous articles about the carbon footprint that hemodialysis creates. It's estimated that in Australia, there was a paper estimating that the carbon footprint from dialysis units is about 50% of the individual carbon dioxide excretion of the entire population of Australia. So not using water, not having the RO units, not having the entire hemodialysis infrastructure would also help in that regard. And in addition to these configurations, the technology could potentially also be used to regenerate PD or hemodialysate without needing a sorbent cartridge. And that is shown here. So as an example of what could be done with PD, similar to what I showed that other companies and groups are trying to do, you would have the PD solution infused into the peritoneal cavity, and then the outflow would not be spent dialysate, but would go back into our device that would be used to change the chemistry of the solution more closely back to its original concentrations, and then reinfuse it back into the patient, so that the spent dialysate would be much smaller in volume, and also patients would not have to as frequently instill new solutions into the peritoneal cavity. So similar to what the sorbent technologies are trying to do, but a totally different technology in this regard. And the same thing with hemodialysis. As I said, 6.2 billion gallons of water are used a year in the United States. But using this device, we could take the dialysate that comes out of the hemodialyzer and convert its chemistry much more closely back to the original chemistry that was used in the original infusate, and again, require less dialysate and have less spent dialysate. So these are modalities that we're going to be working on over the next year. These are just some of the folks that have collaborated with me on this project. Roland Ludlow is the CEO of US Kidney Research Corporation, and Jamie Hestigan is a chemical engineer working at the University of Arkansas, and so is Krista Hestigan in the chemistry department, or chemical engineering department, excuse me. And these are some students and postdocs that have also worked on the project with us. And as far as funding, we've received funding from US Kidney Research Corporation, FASN, NSF, University of Arkansas, Health and Human Services, NIDDK. We actually won the Kidney X contest several years ago with this technology. And our current goal is to get another $9 million to be able to finalize the current prototype in 24 months so that we can start human trials. So with that, I want to thank you for listening, and I'll take any questions anyone might have.
Ira, yeah, I actually have two questions. One with regard to urea, the other with electrolytes. So with the with the ultrafiltration module, when you ultrafilter fluid, the urea in the ultrafiltrate, I'm assuming the sealing coefficient for urea will be 1, just like with any other membrane. So and you say that in the when that fluid get passed back to the RO module, urea does flow back into the
yes, some of the urea.
So how do you actually change the BUN concentration in the blood?
Well, some of the urea flows back, but another component of it doesn't, is excreted. So it's not all the urea flows back across the RO membrane, or you'd have a futile cycle. You'd be filtering it and then returning it with
Right.
the RO. But that doesn't happen. Only some of the urea goes back. And as I said, we're working on RO membranes that will be completely urea impermeable, so that everything that was filtered through the ultrafilter will be excreted. I mean, to get rid of 25 grams of urea at a BUN of 10 milligrams per deciliter, you have to filter 250 liters a day. Right? We don't have urea transporters like the nephron does. So to get rid of about 25 grams, which would be sort of an average protein intake at a BUN of 10, you need to filter 250 liters a day. And our ultrafilter membrane can go up to 800. So we're not limited by the rate of water filtration through that ultrafilter. Right now, the issue is that we're not excreting all the urea because we're losing some back into the blood in the RO filter. But as I say, people have published papers on making RO filters that are basically urea impermeable. We just haven't tried those yet.
So how much of it goes back?
Right now, about 60–70%.
Okay.
So,
Okay.
but again, if you do the math, if the BUN goes up in the blood and everything else is managed, let's say appropriately, it's not going to be very dangerous for the patient.
Okay. My other question has to do with
I have other questions, if possible. This is Victor Gura.
Oh, hi, Victor. How are you?
I am fine. I enjoyed very much. Welcome to our club. It's a tough project, what you have started. A couple of months ago, Jamie has taken your associate, showed in the Asylum meeting your device, and what I saw weighed 30 pounds without batteries. So I assume that the 12 pounds you showed has not been built yet.
No, it's been built.
It's been built?
Yeah.
Then I wonder how you miniaturize that. The other question is, I didn't see use of heparin here. And how do we prevent things from clotting?
Right. So two good questions. One, we have a number of devices. I wasn't at that talk, so I don't know which one he showed. Miniaturizing the components, we don't feel is going to be a major problem getting below the getting to the 12 pounds. The difficulty will be getting to the size of a native kidney to implant it. That's going to require a lot of thought and potentially new technology. So I don't think the size, and also our goal is not to have this wearable, it's to just sit on a desk. So whether it's 12 pounds or 20 pounds, it's not something that we think is going to be significant, because we envision the device being used on a night table at night if the patient wants to dialyze at night, or use it at work, but they'll leave it on a bench or their desk at work. We don't envision them walking around with it. So we don't feel the absolute weight is crucial for at least what we're trying to do. And as far as the blood clotting, in the pig study, we used the polysulfone membrane, and that required heparinizing the animal. But our new nanocellulose membrane is quite remarkable. In the studies we've done with blood, it does not clot compared to polysulfone. And as I say, we have a patent on that. I can't get into a lot of details, but it has anti-fouling properties that are quite remarkable. What will be needed, though, is to work out ways of having the tubing coming from a CVC into this device from clotting. So, we're working on that also to try to create plastic lines that will be going as part of a CVC that will not clot. So it is an important question and an important problem, but we're working on it.
It was a great talk.
Is the issue, I don't know if you saw the paper from the Dutch group that came up, I think, in a couple of weeks ago, in which they showed that running electrical currents through a dialysate with urea creates H's, advanced glycosylated end products, which are known to be toxic. And that sort of throws a monkey wrench of some of your competitors trying to use electro decomposition of urea.
Right, it's a major problem, but they're using much higher currents. The currents that we're using are like 20 milliamps. 20, 30 milliamps. They're very low currents that are needed to run these electrode deionization units. So at least with our device, we don't think that's going to be an issue. But there are people, as you alluded to, trying to get rid of urea using high high electric currents and voltages, I think the mixing chemistry is probably the most viable as far as safety. And I know you were working on one of the papers with that that chemistry. To me, that's the most exciting in the urea removal field.
You may want to check on ages anyway, because FDA is going to ask you. So if you don't think you make them, you may have to prove it, because our mutual friends in FDA for sure are going to come up with that question, which is one of many ones. Another one is human factors, in which the interaction between your device and humans is a very big deal. And patients are going to tell you, how do you expect me to walk around with this? Where do I put it? Do I want to walk around with this and go to the supermarket? Can I go to work with this? There are patients that say, I want to rappel from in a rope from the top of a hill with your device, or go canoeing. So human factors is going to be a big deal. And that's coming down the pike for the device that you showed in your video, which is not bad, but that's a whole new.
Yes, I mean, you make another good point. Any device that you have interacting with the human is going to require toxicity studies, biocompatibility studies, costing millions of dollars. I mean, that's the game. So, we're well aware of that. Again, with us, we're not thinking of this being carried to a supermarket or being worn. It would be used as a PD cycler at night when patients are sleeping, or during the day if they want to use it at work. But again, the points you make are good ones.
I have another question against the electrolyte. So the blood that goes to the EDI module will be free of, let's say potassium. Let's say. So if you pass the blood containing potassium to the EDI module with the selected potassium, the blood is coming out is free of calcium. Free of potassium, and that blood will get returned back to the patient. How do you control for the K concentration of the patient? How do you prevent the K from being too low, for example?
Right. So we have what we envision and what we have now is a sensor bank measuring the ion concentration of the major cations and anions coming through the ultrafiltrate. We don't want to have the sensor bank interacting with blood, because then you have issues of calibration changing, clotting of the electrodes, this sort of thing. So the sensing of the ion is done right after the ultrafilter, and we have the ability to have feedback. We can modulate the transport rate and selectivity of these EDI wafers, such that on a time scale of minutes, we can modify their transport rates based on the blood chemistry to keep the blood chemistry within defined software limits. That's sort of the idea, not just with potassium, but other ions also.
Wait, so you're measuring?
We're measuring the major ions continuously.
Oh, okay.
With feedback control.
Okay.
Yeah. So the idea is that the device's function is not static. Patients eat, their blood chemistry is constantly changing. So we have to have the functionality of dynamic control based on changes in blood chemistry.
So the device actually measures.
Yes. We're measuring sodium
continuously.
Yeah.
Okay.
We don't have now a urea measuring. Urea is hard to measure. I don't have time to get into it now, but ultimately we want to have a urea sensor too, so we can measure the BUN on an ongoing basis. So it differs in that sense from current dialysis machines, where you're basically treating a patient blindly. You don't really know what you're doing until you measure the analyte concentrations much later. Here we envision having real-time online dynamic measurements that is needed for the functionality of the device.
Okay.
Ira, this was an extraordinary presentation, and I was just in awe of it. I have two questions, one specific and one a bit more general. The specific one is I missed how you deal with the middle molecules that are so important that this is a wearable kidney. And that takes me into question number two, which is, do you envision this as a wearable kidney, a kidney transplant, or do you envision this as essentially a bridge, something where between a dialysis unit and a kidney transplant?
Yeah, so two good questions. As far as the middle molecules, we've done some studies. I was alluding to the study with lysozyme, which is a good surrogate that is used for middle molecules. Although there's a controversy as to what actually the size of a middle molecule is. Some people say it's from 550 to 2,000 Daltons. Others say you have to go up to 60,000. There's a huge controversial literature on what are the toxic middle molecules. It's really a mess, whether it's beta-2 microglobulin, light chains, pentraxin. There's a whole slew of them. No one really knows very much about what is actually causing the toxicity to the kidney and to the rest of the body. But at any rate, our goal is to see what middle molecules we are able to filter and excrete. They won't be transported. Most of them are neutral, so they won't be transported by the EDI unit. So basically, it'll all be up to the ultrafiltration module to have the right cutoffs to be able to excrete a certain repertoire of middle molecules. As I say, we had a favorable study with the lysozyme where it was all permeating through our membrane as opposed to polysulfone. So we were happy with that. There will be some middle molecules though that we excrete. There'll be others that we don't. We're just going to have to do more studies. As far as the how the device will be used, we are not working on a wearable device. We envision most human beings not wanting to wear anything. In our view, people will want to use it on the table, and whether that table is a desk at work or at night when they're sleeping, that's how we're envisioning our portable device. We also envision the technology potentially being used in a dialysis unit, but instead of a dialysis machine, you'll have this device that won't require any water or a dialysate or a dialyzer. So that's a third configuration. And as I said in the talk, the last two are in people that still would continue with dialysis, but to try to enhance the efficiency of PD and hemo, not needing as much dialysate by returning the chemistry of the dialysate more close to its original chemistry using our technology, instead of the sorbent technology, which is basically a binding technology. The idea with the sorbents is bind everything, bind the urea, bind the ammonia, bind the phosphorus, and then change that cartridge every so often. We would be doing it in a different way with the components that I detailed in the talk.
Ira, how do you, this is great, I love it. How do you envision the device connected to humans, if that's a portable, to do it at night? Where do you see the connection?
I see it as a CVC, at least for the portable external devices. If it's someone who's, if we're talking about the dialysis unit where the device, the technology is used to enhance the efficiency of hemo, or it would be, through an access. With PD, it would be through a peritoneal catheter. Yeah. Ultimately, it would be hopefully implantable. That's why we started this project.
Yeah.
To create.
Have you infused in the in vitro system any hormone like PTH or something that just to see the change of the calcium or phosphorus? Do you play a little bit with that? Not yet.
Not yet. Not yet. Not yet.
It's great.
We have measured the calcium excretion rate.
I saw it. Yeah.
It's good. It could be better. We have to do. We'll be focusing on the excretion side to see whether changes in the blood chemistry that we do can result in appropriate changes on the excretion, either up or down. I
was surprised on the change on the phosphate. It seemed that there's something is different than the other one. Do you have any?
Yes, the phosphate goes in the other direction, and that's just because the efficiency of the phosphate getting through the anion exchange beads that have an affinity for phosphate just change their affinity in the opposite direction. It could be that there's more as you increase the current with phosphate, there's more competition with other anions, so that phosphate can be transported less efficiency. At least that's the explanation, that you're increasing the competition with other anions that now get transported prevents as much phosphate from being from being transported. So yeah, that was surprising.
Yeah, thank you. That was great. I love it.
Ira, I have a quick question for you. You know, when I was a fellow, there was this old machine in the dialysis unit called the Ready that when you talk about footprint and all of this stuff, I mean, this was an old machine, but it used so much less water. You
Yes.
could regenerate the dialysis.
Yes.
Why did that get abandoned?
The Ready machine actually, I think, was created, and Isidro might be able to help me with that. I think, wasn't it Roberts was his name? Isidro?
Yes, Robert.
Yeah,
Yes.
he worked where
He was at the VA with
the
the
VA in the Valley, yeah.
Yeah.
So no, that was an advance. And if you think about it, all the groups that are trying to create wearable PD and even the wearable hemodialysis devices, all are using a sorbent-based module to bind urea, to bind all the ions that you don't want to have in the dialysate. It's the same concept. So no, the Ready machine was an advance.
Actually, the Ready machine was invented by Larry Marantz from Caltech in collaboration with the group at Cedars. And I think Marty Roberts in those days was involved, but it was Maxwell and a few other guys at Cedars that started the Ready. And it's about 20 years already that there is no Ready, which is regrettable. And that was closed because of commercial reasons that have nothing to do with the usefulness of the machine.
Yes, I mean, you know, when I was a fellow, we were using that all the time. When I first came to UCLA, we were using the Ready machine. I'm sure Isidro did also.
Oh, quick question. Can you talk a little more about the access? Is it through a CDC?
Oh, yeah. So,
this is from Dr. Wase, who.
Right. So that's something that we must work on, that we're putting a lot of thought into, because our goal is to have a patient use this thing who's not heparinized or who's not on an anticoagulant. And so even though the ultrafilter, the nanocellulose membrane we're working on, has fantastic properties as far as not clotting like polysulfone and other membranes, we still have the weak link, which is the access, the CVC. And so we're working on taking some of the chemistry that we're using in the nanocellulose membrane and designing a new CVC that won't clot. And that's something we're working on currently. Because if we can't solve that, we're going to have to anticoagulate the patients, which we don't want to do.
Sounds
ultimately, if it's implantable, you know, we won't be facing that access issue. But right now, it's an issue.
And then where are we with the timeline of this? Like when do you
Well, as I
think?
say, it all depends. Frankly, it all depends how much money we have for the project. So we've budgeted another $9 million or so. If we can get that kind of money, we can have a working final prototype in about 24 months.
Oh, that's fast.
If we don't get the money, it'll take longer. We know exactly what we have to do and we know how to get there. It's just a matter of financing the project.
Is it mainly NIH or pharma?
No,
or
it's private investors, it's venture capital. The NIH is just, you know, you're not going to get $8-9 million from the NIH. So no, I mean, it's a risky project. And so, I mean, Victor knows how difficult it is to fund these things. So it's an ongoing issue, how to fund projects. If you think about it, it's crazy because the federal government is spending last year, $114 billion with a B, on kidney care, which is 20% of the entire Medicare budget. And these projects obviously need far less money and would ultimately save billions if any of them came to fruition.
Not to frighten you, we earn 40 million.
Well, when you get into the human trials, you're spending 40, 50, 60 million.
Yeah, that's where a lot of the money went, but
right. It's the human trials are extremely expensive. Forget creating the device.
All right, excellent presentation, lots of discussion, and we're probably interest of time. We're at the end. So thanks again. And then please, everyone, fill out your evaluations, the pre and post tests, as well as the overall. Look forward to it. Thank you, Dr. Kurtz.
Thank you, everybody. Thanks.